Welcome back, everyone. You are seeing a simulation of 1,000 compound double pendulums, one for every subscriber. Thank you all so much for liking, commenting, and sharing my videos. Now let's compare this to a simulation of 1,000 simple double pendulums. We can see that both systems are chaotic because after a few seconds, the pendulum positions are wildly different, even though they all started within 0.5 degrees of one another. In today's video, we will learn how to model, simulate, and animate both the simple and compound pendulum. Then we will have some fun and create the beautiful slow motion animation shown on the screen now. All code can be found on my GitHub in the description below. As always, I'm Logan and I hope you learned something new. Let's get started by modeling the equations of motion for the simple pendulum. We see that for the simple pendulum we have masses m1 and m2, and they're going to be connected by rigid rods L1 and L2, and they'll be pivoting about this point right here. We'll define theta 1 as the angle from the vertical axis, and theta 2 is going to be defined relative to L1. We'll define our world coordinate frame to be from this pivot point, with the x going to the right and y going up. Our goal now is to write down equations for the positions of m1 and m2 as a function of theta 1 and theta 2. I'm sure most of you could go ahead and just write down the equations for m1 and m2, but I'm going to show you a very elegant way that we often do this in robotics. We're going to do this using something called coordinate transforms or homogeneous representations. We're going to get started by defining this A-frame to be the position of mass 1. Then we're going to define this coordinate transform TSA to be a 3x3 matrix, which allows us to represent any vector in the A-frame in terms of the S-frame. And we do this just by right multiplying TSA by our vector in the A-frame to transform that into a vector in the S-frame. So you see that we have two different components. We have this rotation matrix, which simply is the rotation between S and A. So you see that is just the rotation about the Z-axis, which is, in this case, out of the screen, about S. And we're going to be rotating by theta 1. Then we have this PSA, which is the distance in terms of the S-frame from the origin of the S-frame to the A-frame. This might take a little bit of getting used to, but you'll see shortly why this is so worthwhile. So we can write down the position as this TSA times 0, 0. So of course the position of mass 1 in the A-frame is just the origin, so it's 0, 0. And whenever we do this homogeneous representation, we always have to append a 1 at the end. Okay, then we can define the velocity as just a derivative of p1. So velocity is going to be a 2x1 vector, and p1 is also a 2x1 vector. Okay, now let's do the same thing for the B-frame. We can define TAB, the transformation between A and the B-frame, as this RAB and this PAB. So PAB is shown in red, and RAB is this rotation matrix. And you'll notice how similar TSA and TAB are, and that's very convenient for us. So because TAB allows us to write any vector in the B-frame in terms of the A-frame, and TSA allows us to write any vector in the A-frame in terms of the S-frame, we can write any vector in the B-frame in terms of the S-frame simply by right multiplying TSA by TAB. Perfect. So now P2 is just going to be TSB of 0, 0. And that's because mass 2 is located at the origin, or 0, 0, of the B-frame. So we're transforming this guy all the way to the S-frame. So now P2 is just going to be the vector in the S-frame going from S all the way to B. Perfect. Now we can write V2 as just the time derivative of P2. So what we have are P1 and P2, V1 and V2, and all of these are 2x1 column vectors. Perfect. Now let's move on to the compound pendulum. This is going to use basically the exact same math, but we have to take into account a few more things. So with the compound pendulum, we don't have point masses. Now we have rigid bodies. And rigid bodies have inertia. So inertia is the resistance to angular momentum. So it's more difficult to rotate these guys. So we're going to assume that the rods have length L1 and L2, masses M1 and M2, and their moments of inertia about the center of mass is going to be I1 and I2. If we assume that the rods are thin, then we can estimate the moment of inertia by the formula 1/12 m times L squared. So this J is either a 1 or a 2. Okay, now let's put down theta 1 as the angle from the vertical and theta 2 as the angle relative to L1. Now we'll define our coordinate frames S, A, and B like before. Write down TSA, TAB. Notice these are identical to before. We have TSB as the exact same product. Now this is the difference. The center of mass of this first rod is located half a length up on the y-axis in terms of the A-frame. So we can write P1 as TSA times this vector going from A's origin up to this gray circle. And that, of course, is just 0.5 times the length of L1. P2, same story. We go with the B-frame, we go up 0.5 times L2, and then we write that vector in terms of the S-frame using our TSB. Then V1 is just P1 dot, and V2 is P2 dot. So same story here. P1, P2, V1, and V2, they are all 2x1 column vectors. Okay, so now we're ready to plug into the Euler-Lagrange equations. So for the compound and the simple pendulum, it's the exact same thing. The only difference is for the simple pendulum, of course, the moment of inertia is 0 because point masses don't have a moment of inertia. So we have the kinetic energy, 1/2 mv squared, and then we have the rotational kinetic energy as well. So whenever we have rigid bodies, we're going to get these terms right here. Okay, now the potential energy, this is just mgy of the centers of mass. I wrote this as P1 transpose times 0,1. That's just going to extract the y coordinate of the position. So for the compound pendulum, this is P1y, this is P2y, and for the simple, this is P1y, and this is P2y. Perfect. Lagrangian is just going to be L equals T minus V as always. And then we'll plug into the Euler-Lagrange equations. So solving these by hand is kind of a nightmare. I've done it before. It takes about 6 pages to do it. So we're going to use our friend Python and SymPy to do all of this for us. And we'll see how those coordinate transforms lend themselves very nicely. Now we're going to use Python to solve the Euler-Lagrange equations for the simple and the compound double pendulum. We'll get started by doing some basic import statements. Then we'll go ahead and define our symbolic variables. These are going to be constants. If you'd like, you could set some of these to whatever you'd like, or you can just leave them as symbolic variables. I'm going to set them all to equal 1. Now we'll go ahead and define theta 1 and theta 2. So these are going to be functions of time, so we use dynamic symbols. Then we'll take some derivatives. This will just make writing down some code easier later on. Now we'll define our coordinate transforms. We have TSA, TAB, and of course TSB. And remember, in NumPy, you need to use the @ symbol to do matrix multiplication. Do not use the star symbol. That is a very different type of multiplication. We'll go ahead and write down P1 and P2. So for the simple pendulum, this was just TSA times the 001. And then for the P2, it's TSB times 001. We'll go ahead and get the velocities, V1 and V2. We have to do this element-wise. You could do this using a list comprehension as well. Then the total energy is going to be 1/2 mv squared plus 1/2 mv squared. So then we can do the potential energy. Notice I'm just extracting the y coordinate of P1 and P2. We'll write down the Lagrangian. Then we'll simplify the Lagrangian. If you don't use these simplify commands, then what's going to happen is your expressions are going to get very long. Then our solver is not going to be able to actually obtain an algebraic expression. So use simplify. Then we'll write down the Euler-Lagrange equations. So you see they're very easy to write down here. Again, we'll simplify these before getting into the solver. And then we'll just tell our solver to solve equation 1, set it equal to 0, set this guy equal to 0, solve them for theta 1 double dot and theta 2 double dot. Then we're just going to simplify the answers. And if I hit run, going to take a few seconds. There we go. So theta 1 double dot is this nice expression, and theta double dot 2 is this guy. So this is a lot. If you wanted to, you could write this down and type the code out, or we can make our life easy by running this code below. So I'm just going to run this so you see what the output is. So you see we can just copy and paste this into another script. And let me just scroll through this. So I'm defining G to be this theta 1 double dot and theta 2 double dot. And all I'm going to do is I'm going to substitute the symbolic variable theta 1 with the string, the text string theta 1. Then same with theta 1 dot, theta 2, and theta 2 dot. Then I'm going to go ahead and replace these sign terms with numpy dot sign. That's just going to save me the hassle of manually typing np dot every single time we see a sine or a cosine term. So with that, we could just copy and paste this right here. One trick is if you actually put a print statement here and run this, then it makes it a little bit easier to copy all that. So cool. Now we've done that for the simple pendulum. Let's go to the compound pendulum. Okay, so this is essentially the exact same file, and I'll just highlight the differences. So we're going to define I1 and I2 are moments of inertia. Then this is all the same, all the same, all the same. You see P1 and P2, instead of being 0, 0, 1 and 0, 0, 1, we have this L1 over 2 term, and that came from the fact that the center of mass is in the center of the rods. So the y-coordinate is L1 over 2, this y-coordinate is L2 over 2. Total kinetic energy, this is the same. We just have to add the 1/2 I theta 1 dot squared and the 1/2 I theta double dot squared. And be sure to use the double star for squaring things. Don't use the caret symbol. That is not times in Python. This is the same. This is all identical. So let's just go ahead and run this. And then theta 1 double dot, we have expressions for this guy, and theta 2 double dot. Perfect. Let's do the exact same code. I'll put this print statement in here and run that. And you see now we can just go ahead, copy and paste this into the next file where we're going to actually simulate the double pendulum. Now that we have the equations of motion, let's go ahead and simulate the simple double pendulum. We'll get started by making a new Jupyter Notebook file and doing some import statements. Then we're going to define our system ODE. So y is going to be our state vector. This is going to have theta 1 dot, theta 2, and theta 2 dot. Then we just need to define theta 1 double dot and theta 2 double dot. And this is what we did in simple derivation. So just go ahead, go back to that file, and then go ahead and copy and paste these guys into here. Perfect. Then we'll go ahead and we're just going to simulate this and plot the result. So we're going to do this up to 15 seconds, and we're going to be sampling this at 30 frames per second. X naught is going to be our initial condition. So theta 1 is going to be pi over 2. Theta 1 dot is going to be 0. Theta 2 is going to be 0.001 radians. And then, of course, theta dot 2 is also 0. So we'll go ahead and we'll simulate that. We'll grab the output of a solver. Then we can just create a very simple figure with two subplots. And looking at that, you can see we have theta 1 and theta 2 as functions of time. Okay, now let's go ahead and create an image of the simple pendulum in a particular state. So I'm going to go ahead and grab this line 2D object. Then I'm going to create a new figure, and we're just going to hard code theta 1 and theta 2 for now. We'll go ahead and get P1 and P2 using our coordinate transforms. Then we can go ahead and set up the origin, the black point, then the mass 1, which is blue, mass 2 is red, then the sticks going from the origin to the blue, then of course the blue to the red. So that's done right here. Perfect. We'll just go ahead and show that. Next, we'll go ahead and animate the spring pendulum. So we're going to actually grab all of the solver output right now, so theta 1 and theta 2 and time. I'll make a new figure. Then what we're going to do now is we're going to define these handles just as we did before, but it doesn't really matter where you place these at the beginning because we're going to update them. So right now they're all actually just 0, 0, since I set everything to be zeros. So then for each frame, what we're going to do is grab the new theta 1 and theta 2. Then we're going to update P1 and P2 using our coordinate transforms. And then we'll simply move the mass 1, the mass 2, and then redraw the sticks. And we'll do that for the entire simulation. So when we do that, we're going to get this nice GIF file. And if I want, I can actually open that up. And you see we have this nice little animation of one simple double pendulum. Okay, now that we have it for 1, let's do it for 1,000. So I'm going to get started by doing some imports, and I'm going to actually import the MoviePy library. This is going to help me make some MP4 files. I'm also going to grab this HSV2RGB function from Matplotlib. So you see here I have 1,000 double pendulums, and I have this double pendulum class. So I'm going to create 1,000 instances of this double pendulum class, and every instance is going to run its own solve IVP. It's going to store the theta 1 and theta 2 as functions of time. And it's also going to have access to all the different Matplotlib handle graphics. So let's go through the rest of the code real quick, and then I'll come back up to the top. So we're going to get started by defining 1,000 double pendulums, all with different initial conditions listed right here. Then we'll go ahead and simulate all of these double pendulums. So when that's done, I'll create a figure. I'm making this 1920 by 1080 pixels. So this is the figure size, 19.2 inches. Then we're going to have 100 dots per inch. So that's going to give us the full 1920 by 1080p. Then I'm going to set the x and the y limits. I set this divided by 7. What's important here is that we have the same aspect ratio for the x and the y as we do up here. And it's also important that we can see the entire double pendulum. So I'll scroll down and give you guys an image of this. We want to make sure that these double pendulums are not going off the screen, so that's why I divided by 7. If you could divide by 6 to kind of zoom everything out a little bit. Okay, perfect. So then I'm just going to create the background. Then for every pendulum, I'm going to create a new color. And then I'm going to assign a mass and some sticks to all of the pendulums. And then I'm going to call this assign handles function in order to save the pointer value and give that to that particular pendulum. So I'm going to scroll back up real quick, and you see that when we do the assign handles, we're just saving these handles to our object. And then when the update handles is called, we simply grab the new theta 1, theta 2, we get the new P1 and P2, then we can just update mass 1, mass 2, stick 1, and stick 2. So that's how we do our animation. So last thing real quick, we're going to use this make frame function. So this is what we're going to use with MoviePy. And so we're going to just stick the make frame function into here in this video clip object. Then we're just going to simply write the video file to an MP4 file. So I'm also using this global keyword right here. So this is not the best practice, but this make frame, it takes in a time instead of a frame number, and it's just a little bit easier to iterate over 0, 1, 2, 3 instead of going over t equals 0, t is 1 over 30, t is 2 over 30 for 30 frames per second. So that's all that is. So if I go ahead and run that, it takes a minute to run, 3 minutes actually, but we'll get a nice screenshot of the final slide, and we can actually go ahead and look at this now. So this one's 15 seconds, and it just creates this nice animation. You've seen this before, and if I fast forward, you can see this. Perfect. Let's go back now and do a slow motion version. So the only thing I'm going to change is I'm going to add this speed term. And so what we're going to do is we're going to simulate only for 10 seconds, but then we're going to evaluate our ODE just 4 times more often. So we're going to now evaluate this guy 120 frames per second instead of 30. So everything else is pretty much identical, just the number of frames is increased by a factor of 4. If I scroll down, this is all identical. This is all identical. This is all identical. Perfect, perfect. You've seen this before. Now the only difference here is that for our animation, I'm now doing this duration of t final divided by speed. This is going to give us 40 seconds of our video, but we're still going to run this at 30 frames per second. So the way this works is that this video file, this is going to be 40 seconds of video, but we're only showing 10 seconds of the actual simulation. That gives us the 4 times slowdown. So this one took a very long time, 8 minutes to run on my computer. And this is the last frame. And if I go ahead and I look at this video, you see it's 40 seconds long. And I'll just skip ahead to the fun part right here. So you see how it's really slow, and we get this 30 frames per second, but it's going 4 times slower. So That's exactly what we want. So that's perfect. Now let's go ahead and simulate the compound double pendulum. This is basically identical to the simple double pendulum, just with a few tweaks here. So the first tweak is that we have a new ODE. So go ahead, rename this, and also grab the new theta1 double dot and the theta2 double dot from our compound derivation.ipy notebook. So just go ahead, copy this guy into here, and we'll be good. Everywhere you see solve IVP, you're going to replace that with the double compound pendulum ODE from now on. So we've done that. We'll just go ahead, run this, and you see we have this nice simulation. That looks good. Now we can go ahead and create this little animation here. So what we're going to do is we don't have the masses anymore. You see the mass here is gone, the mass there is gone, so I just deleted them. So we have a stick 1 and a stick 2, and that's it. Everything else is identical except for the title. So we'll move on to the next part. This is going to be creating the GIF file. You see there's no masses anymore. And everything else should look pretty much identical to as before. We just have the stick 1 and then we have the stick 2. So I'll do that, and I will actually open that up now. And you see we have this beautiful little animation of one double compound pendulum. So now that we can do one, we can do 1,000. So let's go ahead and import MoviePy just like before. Everything is really the same. We just have the new ODE right there. And now instead of having the masses, we just deleted them. So stick 1 and stick 2. That looks good. And then updating the handles, we're just setting stick 1 and stick 2 because the masses don't exist. Everything else right here is the same. The first difference we have though is this rainbow color. So before it was blue, but now I'm using a whole spectrum of this HSV. So I'm just sweeping over the hue values to give me a rainbow. So if you don't know what HSV is, it's super easy to use. It's just an alternative to RGB. So here's an HSV color chooser. If I go ahead and I set the value and the saturation, then you can see these are all the different hues. So a hue of 0 is red, and then we sweep through the whole rainbow, and we go to this kind of purple fuchsia, and then it goes back to red at the very top. So all you have to do is call the HSV, and so for the first pendulum, it will be red, and then we're going to go all the way to yellow, and then green, and then blue, and then pink, and then back to red. So it's going to go through the whole rainbow. So that's perfect. We'll assign the color right there, and then we'll assign the handle graphics, and yeah, we're basically done. So we'll just run that, and you see here's the last frame. I'll go ahead and click on that super quickly. So this is a 15-second video, and you see we have this nice real-time footage. If I skip ahead a little bit, you see here is the compound double pendulums. Okay, we're almost done here. The last thing is to do the slow motion. So same thing, we're going to add this speed term. We're going to increase the number of frames by a factor of 4. Then this is all same as last time. We're using the rainbow color again. That looks good. I just changed this guy to be a compound pendulum. And there we go. Wow, I know that was a lot, but thanks for sticking with me until the end. If you enjoyed this video, please leave a comment below, like and share with your friends. Again, all the code for this video is available for free on my GitHub page in the description below. Thanks again for helping me reach 1,000 subscribers, and I look forward to whatever comes next. See ya.